the last week I think we were looking at the tubular connection behavior. So we will just introduce the design in this few classes. So if you look at this picture, you can see the major parameters that are selected for computation of the capacity is the diameter ratio, which is quite important. If you see the behavior, the ratio of the brace diameter to card diameter becomes large, that means near 1 both. So there will be a different type of failure. If it is small, there will be a different type of failure. If you take a case of a beta is less than say 0.2, very small, that means a very big card, small brace diameter. So what will happen when the load is applied? It will be poking through the tubular, means the failure will be almost local. So if you just make one diagram, if you see this idea, and if this brace is quite small, it is going to be actually failure very much in local. If you do a cross section, something like this, if so this is your diameter of the brace. Now if you just imagine such a small diameter brace only carries little bit of load, and in this kind of scenarios you will get in many places, because you normally do not want to oversize the brace unless it is required. But the card, this could be jacket leg, the leg is designed for some other purpose, by making it to have the piles going through the legs. So you might have a very big leg, but the brace could be quite small. Typical example will be the brace may be 500 mm, but the jacket leg could be 2 meter. So you just come to 0.25, 1 in 4. So that is the kind of situation where you can see the behavior could be almost local. There is no card failure. It is not going to fail like the ovalization, because the load is quite small, and this you might have studied if you have taken the concrete design, punching shear in a column to slab, column to ground slab, or column to roof slab. You might have studied at a certain distance from the column surface, d/2 distance, you see the critical section for failure by shear. So which is called the local punching shear. That means the plate or the slab in that local vicinity is not going to deform, it is just going to go down straight away. Failure is imminent, and which is what we should avoid. So one behavior is the diameter ratio is small, behavior is, or the failure pattern, the idea of the load at which the connection will fail is going to be different. When the diameter ratio is made bigger, so you just go to the same picture, you make it somewhere here. So if you put load again, you see here this is going to be a pattern of failure slightly different, because this is going to ovalize the pipe, because the distribution is larger, taking into account the larger length of the pipe. So you could easily now understand why they have selected the diameter ratio as one of the important parameter, because the failure pattern is going to change. Once the failure pattern changes, the capacity at which it is going to fail also changes. It could be lower. I am not concluding that whether d/d ratio small is going to take lesser load, or d/d ratio higher is going to take higher load. I am not concluding that. What we are trying to make sure is the parameter selected has a larger influence on the capacity of the joint, because it is going to affect the type of failure that may occur prior to failure. So that is one of the parameter. Then we go to the second parameter is the diameter to wall thickness ratio of the cord itself. I think you can very easily imagine, you take is half basically d/2, so r/t, radius to thickness. So if you look at that parameter, the larger the diameter you make, I am sure, keeping the wall thickness, it becomes slender in the sense it is going to be failed by local buckling, very easy to understand, which we have studied in our member design. So d/t smaller is better, but how smaller is going to become too rigid. So that is why the second parameter is also important to see whether it fails by buckling or fails by other means of bending. The third parameter is not so important in the design of basically static capacity. You will see in the equations they will never use this, but this will be very useful in terms of fatigue. Later on we will see in the next few classes the stress concentration at the interface between the thickness of the cord to thickness of brace. So, that really matters, but as a parameter that is also identified during the initial stage of API development. If you look at the previous code, the tau parameter also was there, but recently it was found that this is not influencing the capacity in static loading. So, that is why you will just not see that. Then what other parameters are there? The other parent parameters are basically the angle at which the brace comes and joins the card, which is definitely going to affect. For example, if you take a angle of 90 degree, the total vertical load, it becomes 90 degree means the brace is perpendicular to the card. The load applied on the brace is fully going to deform this pipe in this way. If you make the angle say 45 degrees, I am sure you can easily understand the component normal to the card is less, is getting less. More the angle, it will come near to equal to the axial load on the brace. So, what happened to the remainder of the load? When you have a 45 degree, some load goes normal to the card, some load goes as a axial or inline force to the card. Inline force, I think it's not a problem, it can take large amount of load because big diameter is there. So, the angle is definitely going to affect the capacity because the amount of normal component goes to the pipe is going to be reduced. Then if you have two braces joined together, I think we discussed this one earlier also, the effect of two braces delivering force on the same location is going to have a cumulative effect, which you see this the parameter called the gap. The larger you make the G parameter say 1 meter, then there is no question of any overlapping stresses from one brace to other. Whereas if you make it smaller, then there will definitely be a effect of one of the brace is overlapped onto another brace. That means this location of the card is going to be subjected to higher stresses, but how high depends on what is the loads applied and what is the gap available. But what we do not want, this G you make it bigger, our intention is gone. If you look at, I think now by this time you should have seen some joint, some jacket configurations. You do not want to make that G parameter as 1 meter, then the point is lost, our framing will not come properly. So, you need to keep it closer, but as much gap needs to be there because you need to do welding, because when you look at the welding, both welding will overlap. Weld overlap means is not very good because of the heat generated during welding 2 times, 3 times. For example, you make this one so close that this welding is overlapped onto this welding. Next 2 times you are going to heat, 2 times you are going to degrade the material, and then failure may occur at that location. So, basically I think you can see G also plays a major role only for this type of K joints, but whereas for T and Y joints you do not have such parameter there. So, basically if you see this table is giving you an idea of what is the upper and lower limits of the parameters used in the generation of a empirical formula for the design purpose. So, this is what the experiments were done, FE analysis was done on several joints in almost nearly 1000 testing they have done. If you look at the joint industry project report, they have done 1000 joints fabricated, tested in the laboratory. They spent a lot of money, out of which within these parameters the main thing is 0.2 is the lower to the maximum 1, but we normally in practice we do not want to go to beta value of 1, because you will see when the diameter is equal to this diameter, these points become very difficult to weld. Weld in the sense, if you enlarge that location, basically that is your card, you may have a wall thickness something like this, and the brace also is going to be, this is your center line. So, if you take a plate like this, now you see here this welding, hope all of you can see this welding becomes very, very difficult, whereas if that same thing diameter is smaller, you normally do not have you can weld it properly here, whereas here this is a singular point where the surfaces of the brace and the card is almost matching. So, that is why the d by d ratio of 1, theoretically though it is permitted in the equations, we normally in practice do not keep it to 0.9 maximum, and then you have the tau parameters or gamma parameter, which is basically 10 to 50, angle between 30 to 90, yield I think I explained the other day, the higher the yield is no good for welding, as well we do not have experiments or we do not have the equation satisfying, and the gap cannot be less than 0.6 minus, that means the overlap can be allowed, but not beyond minus 0.6. Now, you see here at the bottom I have given what is the recommendation if you violate this. Basically, you can normally not violate this, but if you have situations where you are unable to go for a better solution, you still allow slightly beyond or the limits, and then calculate the capacity based on the actual, that means whatever the parameters you have, and calculate the parameters using the table here, that means the extreme limits limited by the equations. You see whichever is the lower capacity will be your capacity of the joint. Now, how do we calculate the capacity is basically simple. So, we have a notation, you can see there, the allowable axial load that the cord can take prior to failure. So, basically P allowable is coming from P ultimate divided by factor of safety. So, basically P ultimate is calculated as QF, QU, and then basically Fy, the cord wall thickness divided by sin theta. Now, this is ultimate. So, that is why you see the at the bottom we have a factor of safety defined. So, basically if you have a joint like this, what could be the load that you could apply the cord can take prior to failure is basically your ultimate axial load divided by factor of safety, we have the allowable load on the joint without failure. So, basically this Fs in this particular case there was lots and lots of arguments, in fact several papers have been published in the recent times whether 1.6 is correct or higher is better. Now, remember you just go back to our member design, we were looking at allowable axial stress, is not it, for a short column, not cylinder. I hope you remember what is the value, basically allowable axial stress if the column is non-cylinder, small height, 0.6. So, if you convert the 0.6 to a factor of safety, it will become 1.67, is not it. So, almost similar like, but there is a difference in the allowable stress design. We took the yield as the limiting value, yield multiplied by 0.6 will give you the allowable axial stress. I think most of you might have done in the exam also. Now, there you limited the whole thing to yield point and then you brought down to 0.6, whereas in this we have this is beyond yield and we have gone to first crack, and between yield we are selecting somewhere in between. So, you see here if you go back to our load displacement curve, we are not limiting our capacity at yield, we are going beyond, but not at the first crack. So, we take a slightly higher capacity, but divide by a same factor of safety of 1.6. So, lots and lots of debate was there. In fact, several papers argued that it should be reduced to basically the same as the methodology adopted for tubulars, that means increase the factor of safety to 2.5. But then quite a number of arguments over, then the recent API have adopted, in fact the previous API the factor of safety was 2. So, now they have reduced to 1.6, utilizing the additional strength available in the tubular form, which I think you might have noticed we derived a elastic capacity versus elastoplastic capacity in bending and axial. So, you could see there is a increased strength because of the circular section. So, basically because of that finally the joint committee adapted a factor safety of 1.6. So, suppose if I ask you to find out the ultimate capacity, what you will do? You will not divide by this factor safety. You understand the idea, no? Now, you look at this formula, there are primarily 3 or 4 parameters involved, QU, QF, Fy. I think all of you must understand what is Fy. Fy is the yield strength of cord. Sometimes, not very often, the cord material and the brace material, sometimes we use different strength, but most of the jackets we have all material same. but in case if you have, then you should take the chord yield strength. Remember, this is allowable capacity of the joint preventing failure of the chord, not the brace. That is why you have to use the chord yield stress multiplied by T square, that means the thickness of the chord. So, the bigger the thickness you make, it is going to, it is just a common sense, the stronger you make, it is going to carry higher load. Now, these two parameters are very easy to understand, because thickness and the yield of the chord pipe. Now, you have the other two parameters. First parameter is called the QU, which is typically to account for the geometry of the joint, T joint, K joint, the behavior is going to be different. So, basically to account for the geometry and the load transformation. The second parameter called QF is to account for any stresses in the chord itself. For example, if I take the joint, if I go back to this picture, if I have a load on this brace, as well if I have the load on this chord, the brace load is going to compress, for example, and if you have a tension load on the chord, what will happen? The failure will be earlier than expected. But if you have a compression load on the chord and you have a load from the brace, you can actually see that the failure will not be as early as the earlier case. So, the influence of the load on the chord is going to actually help or increase the effect, basically, because so if you have something like this and you take a T joint, you put one compression load, very simple idea, the local buckling will be preventing from happening, because you got a compression loading exactly at the joint and the other one is also compression loading. So, depending on magnitude of the load that is going to be applied onto the chord itself is going to have an influence on the capacity, whether it will fail premature or it will fail at the ultimate load. So, basically this is the two parameters to account only for the joint configuration and the load path classification, and take into account this. So, somebody have done experiments, have come up with empirical formula basically based on the results of the studies, and you will need to use that. Similarly, in this you will be given an empirical formula to account for it. Now, these two numbers need not be less than 1. The way that the empirical formula is set up, it will be large numbers, not just like less than 1 or less than 2, something like this, because this number ranges from almost big numbers will come. So, you don't have a idea that sometimes empirical formula will limit to 0 to 1, 2 to 5. So, here is a different type of arrangement. So, we need to just see how we can get the values of QU and QF. Similarly, allowable moment, how much moment you can apply at this joint, basically what is the type of moment that you can apply here to avoid failure is a similar typical formula. Only thing is you have seen this, the right hand side of the equation, D is added. So, you can easily understand that larger the diameter, the moment can be resisted by better way, isn't it? For example, if I go back to this picture, the original picture here, if I have a moment here, it is resisted by a coupled reaction from the two sides of the pipe, isn't it? So, bigger the diameter, the decoupled effect will be better. So, that is why you can see here D is multiplied, because to take into account the stability that you will get, and if you do not have that D is very small, what will happen? It will immediately fail. So, the smaller the diameter, capacity or failure could be smaller. So, that is the idea behind, remaining terms remain same. Only thing is QU and QF for moment, the equations will be different, that is the idea. Whereas, when you look at axial capacity, the equations for this also will be different. So, we got two distinctive ideas, allowable axial and allowable moment capacity. All the remaining parameters remain same, even in this you have Fs, you have sin theta, you have yield strength, you have the wall thickness. So, basically I think using this we can decide now whether the joint is capable of taking the load or failing before. So, how is that done? Basically, first let us understand how the formulas for the geometric parameter, so called the joint effect, the geometry of the joint. So, Qu is given for different types of joint. For example, if you go to the left side, we have K type of joint, we have Y and X type of joint. Y and T is almost same, except only the angle is slightly different. And you see here 4 types of loading patterns. You have axial tension, you have axial compression, you have in plane and out of plane bending. I hope all of you understand what is in plane and out of plane. You know, in the plane of the joint, something like this is in plane, the perpendicular to the, this is out of plane, this is out of plane. So, let me just, if the brace is like this is moment in plane, this is moment out of plane. So, you have to just make sure that the whenever you look at the joint, the cord running along, braces are seen, that is in plane, the moment is in plane, and basically the out of perpendicular to the cord is called a out of plane. You will have 2 component moments, of course third one torsion, which normally we do not include in the design. So, basically you see here tension, compression, in plane, out of plane, 4 categories of loading and 4 categories of joint configurations. We have got an empirical formula. We will just spend 1 minute on one of them. Basically, you look at the T joint, simple one, 30 times beta. Beta is varying from 0.2 to nearly 1, and I said do not go to 1, limit to 0.9. So, you can see here this is going to be varying anywhere between probably 0.6 all the way to 24, 25, something like this. So, this number, so basic idea is it is not something like an empirical parameter between 0 and 1 such. So, these will be different numbers for different. So, the larger the d by d ratio, you could see that in the T joints it can take larger capacity. So, that is what the conclusion we are trying to make. So, because if you look at this formula, as long as the Q value is increasing, the capacity is going to increase. So, you need to just understand which parameter is going to help us. Similarly, QUF, these 2 parameters are multiplicative, and the bigger you make, more the capacity is going to be, isn't it. So, you should know which parameter you should put in. Of course, the best parameter in here is the T square. The higher you make, you are sure going to get bigger capacity, square of that, isn't it. Instead of 20, you make it 50, you will suddenly get the very big capacity. So, like this, in this empirical formula, you have got the other loading patterns. Similarly, for K joints, you got another parameter coming is called the gap parameter, QG. This QG is defined as, if you see here on the right hand side, is a parameter relating the gap and the diameter. The more the gap you give, it becomes isolated Y joint. The smaller the gap that you give, basically it becomes a balanced K joint or unbalanced T or Y joint. So, basically that is taken into account. So, the parameter involved is the gap. If the gap is 75, then you can substitute and get it. And the other parameter is the Q beta for X joints. So, first is the T Y joints, highly related to beta and gamma, and basically K joint related to the gap parameter, X joint related to the Q beta parameters. 2 more additional parameters are coming in just to make sure. So, basically if you look at the whole calculation, QU, QF, Q beta and QG. So, of course, QG is used for only K joint and Q beta is used only for X joint. So, these are the 4 categories that you have to look at, and this particular table I will if it is required for examination point, we can print it and give. You do not have to really memorize, but and then you should know how to use it. Basically each load case is different. So, formula is same. For example, if I go to this, whether it is tension or compression, this is the same formula. What you will be replaced is the Q values corresponding to tension or corresponding to compression, and which type of joint you are going to be. For example, when you are designing a T joint, you will take QU corresponding to this If the loading is tension, you will take 30 beta. If the loading is compression, you will take this formula. You understand the idea, no? So, it is a stable only bigger. The basic idea is parameters are going to be calculated corresponding to the joint type, corresponding to the load type, whether it is. So, similarly, you can also look at the in plane bending and out of plane bending for moment capacity. So, we can see, so you can have a large number of combinations of things that can happen. I have just plotted some of these parameters, in fact most of them. So, if you look at the this side, left side is the q u value, that means the vertical axis is q u value, and the horizontal axis I have just plotted to beta for different values of gamma. If you look at, for example, axial X joint, it is dependent on two parameters, one is beta and the other one is gamma, two parameters are involved, and basically for tension and compression you got different formulas, and in plane bending, out of plane bending, two different formulas. I have just plotted for the sake of trying to find out what could be the range of q values that you will get. Just if you look at the right hand side first, the q value for a T joint, there are three colors you can see: tension, compression, and in the compression we have two different values of gamma. Gamma is your d by 2t. So, basically you can see is a band of values. The blue color is basically the tension, it is almost linear because 30 times beta, whereas if you look at the compression, it is just varying non-linearly because it is varying by to the power 1.6 you see here. So, basically it is nearly a non-linear variation, but the values of range you can see 0 to up to somewhere around 35 for the compression loading. For tension loading you have about 30. So, just to give you an idea how these values vary with respect to beta, you can see beta is the primary parameter you can see, whereas with respect to gamma, for example, if you go to this one, in fact the gamma value 10, gamma value 40 is this color, red color versus. So, basically you can see here larger and smaller, the variation is very small. Similarly, I have plotted for 4 cases where X joint tension and compression, K joint tension and compression, and the last one is common to all of them. If you go back to this table, you will see that irrespective of type of joint, in plane and out of plane moments are same, whether it is K joint or T joint does not matter. So, basically that is what you see here in this diagram. So, these parameters can be easily calculated as long as you can classify the joint and go to the table, pick up the right equations and then calculate. Now, QF, the effect of chord load, that means more the stress on the chord pipe, you are going to have the earlier failure or premature failure. It is a little bit complicated, would say it is an empirical formula, very difficult to predict, and that is how they have developed. So, you can see there are several terms. The first one is just the base capacity, that means if there is no chord load, what will happen? It will become QF should become 1. You must remember, if I give you a word no load on the chord, then you do not need to go and calculate and get the value, isn't it? If there is no load, ultimately QF should become 1. If the more load is there, then what will happen? The QF values always have to be less than 1. So, remember, do not go and calculate and get QF value of 10, 20 like this, something must be definitely wrong. The purpose of this is a reduction factor. Basically, you see here, this is an enhancement factor, QU is an enhancement factor, always going to be greater than 1. You saw that numbers, and QF factor is always going to be less than 1. Surely 1 is the maximum when the load is not there in the chord, and the more load you apply on the chord is going to have some effect, whether it is tension or compression, the stress is going to be additive. So, basically little bit complicated formula, but easy to calculate because most of them are empirical. We need to understand the terms. There are 3 constants to be taken. The constants are available from API, they have given for different loading type, different joint type. So, you can just see most of the numbers are 0.2, 0.3 like this. So, these are all calibration coefficients with respect to the card capacity. And then the parameter called A is defined as the collapse load to the yield load. So, basically the PC and MC is calculated using this SRSS formula. Basically MC can be calculated if you have in plane moment and out of plane moment. This, remember, you have to be very careful. This is not the moment and the load on the brace, this is the load and the moment on the card. So, you should be very careful, do not take the load applied here and calculate the QF value. You have to find out what is the load applied onto the you have to look for this load on the card member, not the brace. So, basically sometimes you get confused, take the brace load and apply, which is not correct. So, you have to just look for the load on the card, so moment on the card. So, PC is and MC are the nominal axial load and bending moment resultant. Basically resultant is we have two moments, no, in plane moment and out of plane moment. This card can carry, and just SRSS, sum of squares of square root of both components. So, you can get it. Py is the yield axial capacity of the card. I think what is yield axial capacity? I think we have discussed in few classes before. The capacity of a tubular member until yield is Py, how you calculate? Yield strength multiplied by sectional area. I think we discussed about this many days back. So, you have to calculate the axial capacity by say yield capacity, yield times area, and MP is the plastic moment capacity of the card. So, this also we discussed, and C1, C2 coefficients are going to be obtained from the table in the next page, but you see here the reduced factor of safety of 1.2 instead of 1.6. So, basically there is, because this parameter is only taken, it is not a capacity. So, the factor of safety is parameter is 1.2. So, using this formula, every one of them is available except Py and MP, that is what you are going to calculate. So, very simple. So, this MP is appearing here, Py is appearing here, remainder all will be given. MC can be calculated as long as the moments are given, and then PC is the load applied on the card, which will be given to you. So, now finally we come to when we decide to find out the loads are applied. We have already found the capacity in terms of axial we have found, which is Pa equal to Qu Qf, we have already got the capacity, and similarly moment you may have two components, in plane and out of plane. So, basically you see here moment applied over moment allowable, this is moment applied divided by moment allowable, this is in out of plane, this is in plane, and basically this is the axial. Very similar to, if you remember, I think how did we do the unity check? P by Pa is you just revert back to your members, F divided by Fa, that is what we did, is not it, linear, and then we had Fb divided by capital Fb, which was the ratio of the applied bending stress to allowable bending stress, and then we added the second component, the out of plane. But you see here one funny thing, you have a square term for the in plane bending, and that is what we will see why we have. In fact, there will be square here also, but then after a long deliberation, the nonlinear advantage is not being allowed to be taken for out of plane bending, because there is no much redundancy on this side, because if you look at this, there could be potential distribution of stresses going from longitudinal direction, which is basically the in plane moment, whereas the out of plane moment is quite weak. So, basically the second order term or the square term has not been allowed only for out of plane, but in plane advantage is taken. In fact, if you just go back 10 years, if you see the old formula, which is this 2 is not there, means the square term is not there, because earlier empirical studies proved that the capacity is like that. But now with the improved test and improved lot of computational using FEM, it is now concluded that we could take an advantage of second order. In fact, we will see this, what is this second order, first order. If you can derive this relationship, then you can compare, you will find that this is really true, and basically that is why you will see a square term only for in plane, but not for out of plane. Now, if you just see here at the bottom, for clarity I have just put it for you. Remember, I think the previous class we were talking about classification of joints. I think we did that. We have Y and T unbalanced joints or K balanced joint, and then we have X joint. Now, if you take a typical joint, you may get a combination of them, 50% K for one brace, 50% T or Y for the same brace, and the next brace could be 100% K, which is what we had. Now, how do we compute the capacity? Because we have classified a joint, which is okay, which is just few minutes of exercise, but after classification you calculate the capacities of each category. For example, you take only one K joint, one of the brace is fully K, the other brace is 50% K and 50% Y typically. So, how do we calculate the capacity of the joint? So, you need to come back, calculate the axial capacity using K, axial capacity using Y, and multiply the ratios. 50-50 means 0.5 easy, 30-70, and then put that at the bottom. If it is 100% K, does not matter, full capacity will come. So, what we are trying to do is we try to prorate in this fashion, but of course, there is a lot of argument. Is this correct? Is that behavior going to be just like this? Maybe not. Sometimes as early as 10-15 years back, there was several papers on discussion whether it should be this way or it should be the ratio of each of the category, P divided by P allowable capacity as with respect to say K plus P divided by P allowable of the Y capacity. Both will lead to different results, lots and lots of arguments. Ultimately, API have adapted. Hope I think you have understood my explanation. Basically, you have P divided by P percentage of say K plus percentage of Y. This is basically the capacity of the joint. Just now we have put. You could also have actually P divided by P percentage of K plus cumulative addition. You will get slightly different result, which is ultimately API have decided to go for the second one. But you see here joint classification has by this time you should have understood joint classification has influence only on axial load, isn't it? Of course, the secondary effects also you will see, because when you go to the table for getting the values of QU, you will still select what type of joint, what type of load. But directly you can see here primarily the load path dependency is only on axial load, but not on moments. So, that you need to, so just slowly you have to grasp these ideas so that we can do the simple problems. So, basic idea is we should know how to calculate the P allowable, we should know how to calculate the M allowable and classification. So, three things, if you know the three things, we can come back and check the combined effect should be less than 1. Suppose if you do not have moment, no issues, P divided by PA should be less than 1. So, the next one, after doing this, what exactly we were trying to do a design practice, implementation, design based on axial loads. That means when you make a structure, you have a global analysis using computers nowadays becomes mandatory, because the structures become so big, carrying out a manual design or manual analysis could be taking a longer time. So, mostly you do a 3-dimensional frame analysis, most of you might study in the next few courses. Basically 3-dimensional frame analysis, and whatever the loads that you get from the brace members, you design for it, which is what normally required. In fact, in onshore buildings, bridges, you normally design for that. But what API minimum asks for, you design for that. In addition, you look at the capacity of the brace. Just now we were looking at that so called Py, which is equal to area times Fy, isn't it? Now you global analysis of the structure is carried out, you find out the load is something say P, and also calculate the capacity of the brace member, take 50% and check which is governing. That means if the 50% of the axial load capacity is higher, then the joint must be designed for this 50%, not the actual load. But then there is some problem here. Why should be designed like this? Because the brace is only having smaller load, why not reduce the brace size, isn't it? That is what the question you will ask, because the load is so small, why should we make the braces bigger? There are several situations, for example, material availability. Sometimes what happens is the contractors, they try to make a bigger pipe because that is what is available with them, rather than what you have designed for. You might have designed for 500 mm, they may actually put a 600 mm saying that I do not have that material. So, that could be one potential possibility. The second possibility is the same brace, for example, I think by this time you have a clear idea of how the jacket is fabricated. Jacket is fabricated in a horizontal condition, but finally installed in a vertical condition. Now, during the horizontal condition, the transportation installation time, the brace may be subjected to a large bending, whereas in vertical situation in the final stage it may be only getting axial. So, during the earlier temporary stage you may need a bigger diameter, but actually in the final service condition you may require a smaller diameter, but then you cannot go and change it. Can you change it? It is not feasible. So, you have designed for a temporary condition which is larger diameter, whereas in the service condition you need only a smaller diameter, but unfortunately we cannot change. So, such a situation arises. So, you will have a situation where the load is smaller, but the capacity is higher. Now, why do we do this? Why this API is looking for this? It is very simple, relative stiffness. We need only to carry 100 tons in the brace, but we have made a bigger brace which can carry 500 tons typically, some example. Now, when you have a system responding, the larger the brace stiffness, you will see that the load capture, especially during large displacement, especially like earthquake, during storms, the bigger the brace, even though earlier times the brace is supposed to carry smaller load, it will try to attack more loads, and that might put the joint in danger. So, API have deliberated this one for a long time, finally they have come. In fact, there was a condition in earlier APIs we should design for 100%, especially for large seismic area. Like if your structure is located in a seismic prone zone, then you design for 100% capacity irrespective of what load it carries, which is sometimes very difficult. So, the recent change is basically designed for 50% of capacity and design for the actual load, whichever is giving higher UC is the governing case. The third one is basically the length of the special material. If you go back to our earlier sketches, somewhere I have given you some this kind of. So, what should be the length that you should actually have it in your design, whether you want to have longer is better or shorter. The shorter is not very good because you may not actually distribute the load properly, but the longer is also not so good because thicker material, special material, more money, isn't it? So, we need to have certain guidelines how much minimum should be given. So, API is giving you a easy guidance, as long as you follow that. So, basically the idea is extended by 1/4 of the diameter of the cord or 305, which is 1 foot, whichever is maximum. So, basically if the d/4 is larger, then you must put d/4, not 305, and basically this will give you an idea. But then if you look at this picture, that is to be calculated from edge to the full thickness, not to the tapered thickness, because sometimes tapered thickness could be losing another 100 mm, 200 mm. So, basically the distance A is the one that we were talking about, should be diameter by 4 or 305, whichever is not smaller, larger. And the eccentricities shall be modeled if larger than d by 4. Suppose if you go back to this picture, if in this particular case the work points are common, whereas sometimes you have, I think previously we have seen, if they are joined at the two locations, you do not need to model the eccentricities as long as less than d by 4. Now, this thickened joint, basic idea is how much is better. Just now we saw a minimum criteria of 305 or d by 4, but that is only a minimum condition. But in order to use this full capacity, whatever the capacity, this capacity, all the experiments were carried out by assuming that the distance between the thickened material this was taken as 1.25 times diameter. This is what the assumptions they have made in the finite element analysis and the previous experiments, but now the API says because the reduction of cost is essential, you only go for 305 or d by 4. Now, in order to take into account, we need to do a reduction in the capacity. Basically the last previously calculated capacity from those equations is called PA calculated, is multiplied by a reduction factor, basically must be less than 1 as long as your can thickness larger, totally 2.5 diameter if you provided, then it will become 1, but if it is less than 2.5 diameter, then gradually the capacity will reduce in a nonlinear fashion with respect to the nominal thickness to the local thickness. So, what is TC? TC is basically the increased thickness, which is basically at this location. This location we have a TC, and elsewhere we have T nominal. So, at the distance away it is basically nominal thickness, and the location at which the joint is located is increased thickness is called the increased chord thickness. So, you look at this R value, this is the LC. LC is nothing but the total length calculated by this arrangement. Basically, you will add this length plus diameter plus this length. So, for this type of joint you have both side 2c times 2c plus diameter for the bottom one. The top one you see here 2a, a is here, one more a can allow here plus the diameter, but for the inclined brace you just divide by the sin theta to get the elliptical footprint. I think most of you understand the geometry. So, you have the diameter coming in. So, the length of the or the major axis dimension of an ellipse you can find out by just on simple angle theorems. So, you can see here each brace you need to find out what is the left side, what is the right side, and add it, and that will become the LC. As long as the LC is bigger, reaching 2.5 diameter, then it is not a problem because reduction will not be there. Just to show you quickly before we finish, I just plotted those equations. You can see here the first one, the top one, when the thickness are same, that means the nominal thickness and the chord thickness both same, that means equal to 1, there is no reduction, the load is PA is equal to PA calculated, isn't it? As long as the reduction is there, for example, I make the thickness as 1/4, you can see the blue line, you can see from 1 it comes down drastically with respect to the length of the chord divided by 2.5. So, as long as you have 2.5 diameter as a length, automatically every one of them reaches 1, isn't it? So, this parameter is very important because we normally do not provide so much length.